a geometry. So this is the second section of our probability unit. So this is where we kind of force it and make it actually kind of geometry, because really probability mostly isn't. But we can do a little bit with geometric probability. So that is probability that involves geometric measures. Probability that involves geometric measures. Geometric measures, such as length, area, and volume. And volume. So we can do some probabilities with these. So probability with lengths, the probability that a point falls in a certain portion of a segment is the ratio of the length of the favorable segment to the length of the entire segment. So it's like favorable outcomes out of possible outcomes, only the possible outcomes are all of the points, which really there are infinitely many points on a segment. And so it's the proportion of that line. It is the segment of, the portion of interest. So point X is randomly placed on segment AD below. So I don't know if you can see this real well, that A to D is that segment here in this coordinate plane. On a certain portion of the X is randomly placed on AD below. Find each probability. So find the probability that X is on CD. So CD, the length of that segment is 1, 2, 3, 4, 5. So that length of that segment is 5 out of the overall segment from A to D, which we could count out, or it goes from -7. So 1, 2, 3, 4, 5, 6, 7. This is 8 by 8 this grid to +7. So that ends up being out of 14 for that range. So 5/14 is the probability that we'd be between C and D if we have a point on AD. How about a C? And so we can get that. That is 7, 8, 9. So that is 9 for the length of that segment from A to C out of 14. And then not on AB. So we can figure out the probability of AB, which is 3 out of 14. So it's B1 minus 3 out of 14 would be a way that we could do that. We could do the complement, which would give us 11 out of 14. Point X is randomly placed on PT below. Find each probability. And so we want to know that it's on P to R. And so we're going from 0 to 22. So that is 22 out of the full length P to T out of 40. And of course, we can reduce that to 11 out of 20. QS. So QS, we're going from 14 to 26. So that is a length of 12 out of 40. Which reduces, and we can divide both those by 4, so we'll actually get 3 out of 10, 30% chance. And so you could do the fraction, the decimal, or the percent for these as well. Usually interchangeable unless I ask for one specifically. And then finally, that X is on PQ or ST, so PQ or ST, so in either of those ranges. So that's a range of 14, so it's basically 14 plus ST is going from 26 up to 40, so that's an additional 14, so 14 plus 14 out of the 40, or 28 out of 40, which can reduce, and that will, we can divide top and bottom there both by 4 again, and we actually get 7 out of 10, so 70% chance that we end up in that range. PQ or ST, we also could have done Q to S and done 1 minus that. So that is on lengths. So segment lengths can help when finding probability with waiting times. The probability is the ratio of the favorable waiting time to the maximum waiting time. Draw line segments to help visualize the problem. So a radio station plays a commercial every 16 minutes of music. If the listener randomly tunes in, what is the probability that at least 10 minutes of the music is heard before the commercial plays? So what we can do is here we have a segment here of 16, and so that's kind of the time between commercials there. And so then so I can label this up, so we can go from 0 to 16. I'll split that there, 8, 4, get some marks on here, so that'd be 12, and then split it once more. It'll give us kind of all of our tick marks. So I've got it going by 4s here. We want to get at least 10 minutes before the commercial plays. And so the segment that if we want 10 minutes of listening time, so 10 minutes from the over this 16-minute segment would take us back to 6. So it'd be right there. So that would be 6. So you would have to be in this range. If you start listening in that range there, you'll get that 10-minute segment that you're interested in. And so the probability that this happens is 6 out of 16. So there's a 6-minute range. If you show up, you'll get a 10-minute segment out of 16, which of course we can reduce to 3/8. And so that would be that first probability. A bus stop stops at a bus stop every 45 minutes. Once a person gets to the bus stop, what is the probability that they will wait no more than 20 minutes? So we can give our range here. So we're going from 0 to 45 minutes. So this is kind of how long you might wait. And they want to wait no more than 20 minutes. So I'm just going to kind of speed this along. And if we go 20 minutes back here, so this would be at approximately 25 here. So in that range of 45 minutes, this is when they want to arrive. So they want to be no more than 20 minutes of wait time. And so that range would be 20 out of 45, which we can reduce. We can divide both of those by 5 and get 4 out of 9. So 4/9 would be our probability of waiting no more than 20 minutes. All right, one more example. A store runs a sale exclusively for their club members every 20 days. So our range of time here is 20 days. If Marcus joins the club on August 4th, what is the probability that there will be a sale by August 10th? All right, so we've got our 20-day segment. And so we're going from 0 to 20, and I'll divide this one up a little bit. So we got 5. And 10. So, whoa, what did I do there? 15, sorry. 15, and then 1, 2, 3, 4, get some ticks in there for each of our values. So, what is the probability that there will be a sale by August 10th? So basically, if their sale is with every 20 days, what's the probability that it will be this length of time? So that would be a course of 6 days. So basically, within a 20-day period, in those last 6 days, what's the probability that he would join in those last 6 days before that sale, since this is when the sale occurs. So we need to join there between 14 and 16, so that ends up being 6 out of 20 is the probability that he joins in that specific time, which reduces to 3/10. And so there's a 30% chance that there will be a sale by August 20th. All right, so next we're going to get into probability associated with area. The probability that a point lands in a certain region contained within a larger region is the ratio of the area in the favor region to the area of the entire region. So we're picking a point in this entire rectangle. What's the probability end up in the shaded region there? There are an infinite number of points in the triangle, infinite points, but we still can get that overall proportion. Find the probability that the randomly chosen point lands in the shaded region. So we need both areas. So our numerator of our fraction is basically the area of this triangle, which would be, so the triangle is 1/2 base times height. So it's 1/2 base times height. And so our base there could be 8. So it's 1/2, hold on my eraser, 1/2, sorry. Base, which is 8, times the height, which is 11. So if this is 11, then that would be 11 as well. And so if you multiply that out, we get 44. So it'd be 88 over 2, so we get 44. And then units would be square feet. We don't really need that to solve this, but if you want to be proper about it, that's the area of our triangle. So then the area of our rectangle, really I should say area of, but is just length times width, and so that is length times width, which is 11. We could call the length, it doesn't matter which one we call which. We call that the length 11 times, but then we have to add these two together, 15 plus 8, so that is 23 11 times 23 gives us 253. And so in the end, our fraction, our probability that it lands in there is 44 out of 253. And that fraction doesn't reduce, but you could reduce that to the decimal, which is 0.1739. All right, the next one, let's probably end up in that shaded region. So the area of the shaded region is a bit trickier. It's the area of the shaded. I'm gonna call it A sub shaded. The area of that shaded region we can get by doing the rectangle or the square actually minus the area of the circle. So it's going to be equal. It's going to equal to the area of the square minus the area of the circle. So our area will be the area of the square, which is 8 squared, 8 times 8. And then the area of the circle that we're going to subtract away is pi times its radius. Well, its radius would be 4. So pi r squared, so pi times 4 squared. Which, if we punch that into our calculator, you get 64 minus, this works out to be 50.27. So it's 64 minus 50.27 for that area, and so that shaded region ends up being 13.73, and that's out of the entire area, which is 64. So it ends up being 13.73 out of 64, which works out, if you do that as a decimal, 0.2145. That's that probability to end up in that region. You could do a decimal, you could write as a percent. For that one. Here, our shaded region is the semicircle. So that semicircle, we can find the area. I'm going to write area of the semicircle. And so that is 1/2 of a pi r squared. Its radius is 12, so 1/2 pi times 12 squared. So if we type that in, you'll get 226.19 square feet. I'm leaving the square feet off of most of these. And then that's the favorable region. The entire region is the area of the triangle, which we're going to do 1/2 base times height. So we got that base is 50, so 1/2 50 times the height. So we know that this is 12, that's 12. We also know that this radius here is 12. So the height is actually 24. It's 2 12s. Like this segment would be congruent to that segment. So it's actually 1/2 base 50 times 24. And if we punch that in, we get 600 feet. And so then our favorable region is the 226.19 out of 600, which gives us a probability of 0.377. Last one, the favorable region here, I have a bunch of semicircles, but you could, one way you could speed this up is you could do a bunch of halves of circles, but then you're end up doing 4 halves of the circles, which really combines to be 4 halves is just 2 full circles. So I got to figure those out, that area there. But this one starts out a little bit trickier. We've got this 15, which is the diagonal on this square, right? We've got this square, all 4 sides are congruent, all 4 angles are congruent. So we've got the diagonal of the square. So this is actually a pretty quick application of our 45, 45, 90. And so if this is the 15, that's the hypotenuse side, that's the root 2 side. So we need to divide by square root of 2. We would usually take this times square root of 2 to get that. So we do 15 divided by square root of 2 to get this length. So this, this side length there is 15 divided by square root of 2, which we could be, real exact with that if we wanted to, and rationalize the denominator, and it ends up being, multiply by square root of 2 and so on. But we're going to get to decimals eventually anyways, so we don't really need to do all that to make this any fancier than it is than it is right now. So then we can do the area of we could do the area of the semicircles. So the area of a single semicircle ends up being the 1/2 pi r squared. So you could do 1/2 pi times the radius, which would be half of that. So it's 15 over pi times 15 root 2 over 2, which ends up being like 2 root 2. We can divide that in half. Ends up being just 1, the radius in that square. So pi r and that whole squared. If you punch that all into the calculator, the area of a single semicircle is 44.18. And so then we have 4 of those. So the area of all the semicircles is going to be 4 times. So I'm going to write all semicircles is going to be 44 times that, 44.18. And we would get a total area of, let's see, what is this one? 176.72. So that's our area of our semicircles. We also need the square, area of the square, which is just 15 root 2 times 15 root 2, 15 over square root of 2 squared, which is actually just 112.5. And this is square centimeters right now. And so at the end, that isn't our denominator. It wouldn't make any sense because this area of our semicircles is more than the area of our square there. Our entire area, I actually have to add those together. So it ends up being, our probability ends up being 176.72 over 112.5 plus 176.72. And so if you punch that in, you'll get an overall probability of 0.611. All right, so one more we have here involving area. A dart is tossed and hits the dartboard shown to the left. The dart is equally likely to land it on any point on the dartboard, which is always kind of a weird problem, but somehow somebody's got the ability to hit anywhere on the board. Find the probability that the dart lands in the white area. And so we got to do the area of that, so the area of the bullseye, I guess. And so the area of the circle that we're in, the white circle, white, can't spell, circle, is, the radius is 3, so it's going to be pi times 3 squared, which is 28.27, once we type that in, so pi times 3 squared. And then we need the overall probability, or the overall area of the board, which is the area of the, I guess I'll call it square, which is 15 squared, which works out to be 225, got a little carried away there, 225 square inches, and so it ends up being 28.27 out of 225, which gives us a probability of 0.1256. So that's our probability of hitting the white area. Find the probability that the dart lands in the light gray area. So we want to figure out the entire area of the gray. I'll do the gray circle first. That it hits the circle. So area of the gray circle is pi times its radius. So if this radius was 3, that distance would be 3 as well. So 3 plus 4 is 7. So 7 squared. Pi times 7 squared gives us 153.94 for the area of the gray circle. But we ultimately want we don't want the gray circle, we want the area of the gray ring. Sorry, I can't spell gray the wrong way here. The gray ring, that is, so we don't want just the white, we don't want the area in the white circle, so we basically have to subtract the white circle. So it's 153.94 minus the area of the white circle, 28.27. And so that area gives us the area in this ring of 125.67. And that ultimately is our favorable region, 125.67, out of the same rectangular region as before, 225. And that gives us a probability of 0.5585. Last couple involves some volume, so you got to be able to do your volume calculations. A fish tank with a measurement given below. If the tank is filled with water to a point 2.5 inches from its top, and a point is selected at random in the tank, what is the probability that the point is in the water? And so we want the favorable area out of it. So it's filling up only to 2.5 inches from the top. So Draw that there. This distance is 2.5. And so this distance here, the actual distance that we're filling up to, is 16 minus 2.5, which is 13.5. So the favorable area that we're talking about is the area of the water, I'll call it, is length times width times height for this rectangular prism that's that we're finding an area for. So I'll do 12 times 18 times 13.5, and you get 2,916, and that is, I'll make a note, inches cubed. That's not really necessary, but we'll do that. The area of the tank is that same stuff, 12 times 18, but now we're times the whole height, which gives us an area of 3,456. And so then we just divide those up, 2,916 divided by 3,456, and that probability works out to be 0.84375. And so about an 84% chance that your point will end up in the water. Last one, a sphere fits inside a cube so that it touches each side as shown below, fit perfectly inside there. If a point is chosen at random inside the cube, what is the probability that it lies outside the sphere? So our favorable region is kind of like this stuff on that outer region. So figure out the area of the cube and the sphere. Area of the cube is going to be 14 cubed, 14 to the third power. So 14 cubed, you'll get 2,744, and that's cubic centimeters. The area of the sphere, and so this formula is 4/3 pi r cubed, which our radius ends up being 7. So 4/3 pi times 7 cubed, which works out to be 1436.76 cubic centimeters. So then ultimately our area of our outside region, so our area of our, I don't know, how did they refer to it? Probably lies in the outside the sphere, area outside the sphere. Sphere, so I missed my H in there. The area outside the sphere, we can subtract the cube minus the sphere in the middle, and that'll give us this outer region that's left. So it's going to end up being 2,744 minus 1436.76. If you subtract those, you get 1307.24, and that's out of the entire cube. So it's 1307.24 out of the entire cube, 2744, and you get a probability of 0.4764. So 47.64% of this area is outside the cube, which, yes, I think is a little bit surprising, but that is the proper probability for that one.